Today we are starting a new chapter. The next chapter after that hydrocarbons is your halogen compound. Okay. So as you know that halogens, we have halogen means that the elements which are present in group 17 are known as your halogens. For example, fluorine, chlorine, bromine, iodine. There is one more, but that is radioactive. So we have to study about these 4 elements: fluorine, chlorine, bromine, and iodine. So how they are made, first of all, we have to study the preparation of halogenoalkanes. The first reaction is preparation. So they are prepared by the free radical substitution of alkanes by chlorine or bromine in UV light, ultraviolet light. So you take your ethane C2H6. So this we already have studied that this is your ethane in the hydrocarbon part. So when it is reacted with chlorine in the presence of UV light, so what happens? Reaction will happen. That means HCl will get removed from here. Okay, so you have CH3, CH2, and Cl. So this is the reaction plus HCl gets removed. So this is what? This is our halogenoalkane which is prepared from alkane. So how halogenoalkane is prepared from alkane? By the free radical substitution of alkanes by chlorine or bromine. Okay, so first method is this, and the second method to prepare halogenoalkane is the electrophilic addition of an alkene with a halogen or a hydrogen halide at room temperature. Now we have to do the electrophilic addition. Electrophilic addition means this is your ethene C2H4. As already told you that this is your double bond. That means it have high electron density, right? So electrophile can easily approach this high electron density. So electrophile will come, that is your bromine plus, it will come and it will attack it. Okay, and then we have what? Electrophile from Br will come and we have C2H4. At one carbon we have bromine and another carbon we have bromine. And this double bond is reduced to single bond. So we have C2H4Br2. So the mechanism is different only that in the first part the mechanism is proceeded with the free radical substitution, and in the second part electrophile is coming and it is attacking to the electron density of the alkene. Okay, so if it is bromine, so bromine gets attached to one carbon atom. If it is hydrogen halide, then at one carbon hydrogen is attached and at one carbon halogen is attached, and the double bond is converted to single bond. Clear? Okay, write it down. Here, as we discussed in the last reactions also, that how bromine act as an electrophile here. So we have bromine, Br2. So one act as partially negative, which approach your alkene, and one act as partially positive. So the electron density will shift. Sorry, it will act as partial negative. It will act as partial positive because the electron density will shift to this bromine atom. So this becomes partial positive. So this will act as the electrophile. So the nucleophile will approach the electrophile, and we have this. Carbocation is generated at this carbon. So at this carbon, this bromine will come and attack it.
I'm done.
Okay.
I'm done.
Okay. So next, there are some reactions by substitution of an alcohol. So we have to take these reagents only. That with HX, HX means X means your halogen, or with KX, NH2SO4 or H3PO4 to make HX. Okay. So here this HCl will we react this alcohol with HCl. Then nucleophilic substitution reaction will occur. This chlorine, it will just substitute the OH from this ethanol. Then with PCl3 and heat, we have this reaction. So the byproducts, you have to remember that in H3PO3, the byproduct is H3PO3 when you use PCl3. But when you use PCl5, the byproducts are HCl and POCl3. Next is with SOCl2. So with SOCl2 also, this will substitute, chlorine will substitute OH, and we have HCl and SO2. They both are gases. Okay, so they evaporate. Like they are gases, so they evaporate. So the best method to prepare alcohol is this reaction. Okay, because you get this alkyl halide or the halogenoalkane in good yield. So this question will land up in your exam in 1 mark, that which is the best method to prepare halogen compound. So it is with the reaction with SOCl2 because the two other byproducts are gas. Okay, write it down. Okay, so we have 4 reactions with HX, with PCl3, with PCl5, and with SOCl2. And the best method to prepare this halogen compound is your with the SOCl2 because C2H5Cl is produced in good yield and the other two byproducts are gases. So the chloroethane made in the reactions, so what is the name of this CH3CH2Cl? It is chloroethane because there are 2 carbon atoms, so it is ethane. So it is classified as a primary halogenoalkane, that is 1 degree. If the chlorine is attached bonded to a carbon atom which is bonded to just one alkyl group, if you draw the displayed formula, it will be something like this: CH3CH2Cl. Okay, now see that chlorine, it is bonded to a carbon atom, which this carbon atom, it is bonded to only one carbon atom. So it is a 1 degree alkyl halide. It is a 1 degree alkyl halide. Okay. So we can also make halogenoalkanes where the carbon atom adjacent to the halogen atom is bonded to two alkyl groups, which are also known as secondary halogenoalkanes or 2 degree. Tertiary halogenoalkanes have 3 alkyl groups on the adjacent carbon atom. So these are 3 degree alkyl halides. So you have to you can identify, like if I draw it like this, CH3, CH3, CH2Cl. Alicia, you also cannot hear me?
I can hear you.
Okay, so 2 degree halogenoalkane is this, where the carbon atom, it is this carbon atom which is attached to chlorine. It is again connected to a carbon atom which is connected to two alkyl groups. So this is your 2 degree halogenoalkane. And if we talk about 3 degree halogenoalkane, then what happens in 3 degree halogenoalkane? The carbon atom which is connected to chlorine, it is connected to how many carbon atoms? 3 carbon atoms. Then it is known as your 3 degree halogenoalkanes. So this is my 3 degree halogenoalkane. Is it all right?
Yes.
Okay, write it down. Can you now hear me, Shama?
Yes.
Okay, so we have discussed here the 1 degree, 2 degree, and 3 degree halogenoalkane. So it is very simple. Like the carbon atom which is attached to chlorine, it is connected to one carbon atom, so it is 1 degree. The example of 2 degree is written here, that the carbon atom which is attached to chlorine is connected to two other carbon atoms, then it is your 2 degree halogenoalkane. And in 3 degree halogenoalkane, the carbon atom, which is also known as your alpha carbon atom because it is connected to your functional group, that is chlorine. If this carbon is connected to the another carbon which is connected again to the 3 carbon atoms, then it is known as your 3 degree halogenoalkane or tertiary halogenoalkane.
Hey students! Interested in boosting your studies? Enroll now at Keddy Edtech. We offer online tuition for the Cambridge curriculum, grades 6 to IGCSE, AS, and A-level. Start learning with us today.
Okay, let me again tell you about the examples of 1 degree, 2 degree, and 3 degree halogenoalkane. So remember that this R is my alkyl group. Whatever I am writing, it is alkyl group. Alkyl means it may be CH3, it may be C2H5, right? So this is my alkyl group. So if the carbon atom read this sentence that where the carbon atom adjacent to the halogen atom is bonded to two alkyl groups. That means if this is attached to a halogen or alkane, X means fluorine, chlorine, bromine or iodine. If this carbon atom is attached to only one alkyl group, okay, this carbon atom, then it is known as your primary halogen or alkane. It is known as 1 degree halogen or alkane. So this is the correct example. Similarly, if this carbon atom which is attached to halogen or alkane, it is connected to two alkyl groups and one hydrogen, then it is 2 degree halogen or alkanes. Similarly, if the carbon atom which is attached to halogen, it is connected to all the three alkyl groups, then it is your 3 degree halogen or alkane. It is written adjacent to the halogen atom. Okay, adjacent means here, this carbon atom. So write these examples, not that previous one.
I'm done.
Okay.
I'm done.
Okay, so next we'll read about the nucleophilic substitution reactions. So halogen or alkanes, they are alkanes that have one or more hydrogen atoms which are replaced by halogen atoms, like we have seen for ethane. Okay, ethane is converted into chloroethane. So what is happening in this? Only one hydrogen of ethane, it gets substituted by the chlorine. So halogens are the elements in group 17 of the periodic table: fluorine, chlorine, bromine, iodine. The simplest halogen or alkane whose molecules contain just one halogen atom. So what is the general formula for halogen or alkane? It is CnH2n plus 1 X. Okay, where N is the number of carbon atoms and X is your halogen. Like we have studied the general formula for alkanes. General formula for alkanes is CnH2n plus 2. So what is happening here? One hydrogen is replaced with the halogen atom. So it becomes Cn. For halogen compounds, it becomes, for halogen or alkanes, it becomes CnH2n plus 1 and this one is replaced by a halogen. Then writing?
Yes.
Okay. So the halogen atom has a huge effect on the reactivity of this halogen or alkane compared with that of alkane. So this simply means that the reactivity of halogen or alkanes is greater than that of the simpler alkanes. Why they are more reactive? Because of the polar nature of the covalent bond between the carbon and the halogen atom. Why? Because halogen atom is more electronegative, so it attracts the electron density towards itself, making it partial negative, and carbon will become partial positive. Okay, unlike the non-polar bonds in alkane molecules, but in alkanes we have only carbon-carbon bonds, so electronegativity is same, so it is non-polar. So the carbon bonded to the halogen carries a partial positive charge and a halogen a partial negative charge, because halogen is more electronegative. So in this slide you have to remember only that halogen alkanes are more reactive than alkanes because of the polar nature of the covalent bond between carbon and halogen. Write it down. Done writing?
Yes.
Now see the reaction, how it occurs. Substitution reactions with aqueous alkali. So when an aqueous solution of sodium hydroxide, NaOH, it is heated with the halogen or alkane. In this case, we are taking bromoethane. Okay, bromoethane. There are two carbon atoms, that's why ethane, and bromine is attached, that's why bromoethane. So it is a which type of reaction is this? Nucleophilic substitution. Why nucleophilic substitution? Because OH minus, it will act as a nucleophile and it will substitute. Substitute means it will attach and it will leave the, it will kick the leaving group outside. So OH will attach here in the place of bromine and it will kick the bromine outside, and the Na plus, it will combine with the bromine, so it becomes NaBr. NaBr. Okay, so we have seen here that bromoethane is converted into ethanol. If you want to write down the ionic equation, then in this you have to remove the spectator ions where Na plus and Na plus is your spectator ion. In the ionic form, you can write this like OH minus. When you remove Na, when you remove sodium with a positive charge, then OH negative will remain. When you remove Na from Na, so the positive charge of Na, it will come neutralize here. As you know that NaBr exists as Na plus ion and Br minus ion. Okay. So Na plus acted as spectator ion only. The role here is of only alcohol OH minus, which is the nucleophile, and the Br minus, which is the leaving group. It is the leaving group. So the aqueous hydroxide ion, it behaves as a nucleophile here. Why? As we already studied, what is nucleophile? It is electron rich. It is having a pair of electrons to donate. So it is donating a pair of electrons to the carbon atom, this carbon atom bonded to the halogen in the halogenoalkane. That's why the reaction is nucleophilic substitution. So I hope it is clear why it is called nucleophilic substitution, because nucleophile is coming here. It is substituting the bromine with itself. It is substituting the bromine with OH, and bromine is a leaving group, so it leaves. And Na plus, which is present in the solution, Na plus combines with Br minus to form NaBr. So this is the substitution reaction with aqueous alkali. So we have studied that how to prepare alcohol from halogenoalkane. So this is the method. The nucleophilic substitution reaction is the method to prepare alcohol from alkyl halide. Write it down.
I'm done.
Okay, so these 2 points you have to remember that the fastest nucleophilic substitution reaction takes place with the iodoalkanes, because iodine is the best leaving group. It will leave easily. That's why fastest nucleophilic substitution reaction takes place with the iodoalkanes, and the slowest nucleophilic substitution reactions takes place with the fluoroalkanes, because fluorine is bad leaving group. Not bad leaving group, but less bad as compared to iodine. So write down the order of leaving group. In the nucleophilic substitution reactions, the order of halogens of a leaving group is good leaving group is I minus. Okay, you can write it in the form of halide. Reason is the size only, that iodide ion is the largest. So it is the best leaving group. Chloride is the smallest and less stable. So it is poorest leaving group.
I'm done.
Here you can see that we have CF, CCl, CBr and Ci bond. The bond energy of CF is strongest and the bond energy of Ci is weakest. So it will break easily because it is easier to break this bond. So iodine leaves faster as compared to fluorine, because it is difficult to strong the carbon fluorine bond. Okay, so that's all for today.